Hi everyone. This is the final part of the bridge course which I have prepared. The rest of the things will be taught to you in the regular class itself as and when it is required. In the last class, we learned about basics of differentiation. Here we are going to see one particular application of differentiation, which is basically in calculating the radius of curvature of a function. Suppose this red line denotes one particular function, then you can find out the slope of this function at one particular point. For example, here we have found the slope at the point P on this graph, and the slope was found to be corresponding to an angle which is theta. Now let's take another point on the same curve which is marked as Q and then try to determine what's its slope. And you will see that that particular slope line will intersect the x-axis at an angle theta plus delta theta in this particular case. Now from the point P and Q, we draw perpendiculars as shown in the next case. These are perpendiculars drawn from P and Q, and these perpendiculars meet at a point which we call it as point C. Now, if this angle is very small, we can show exactly by geometrical argument that this angle also will be equal to delta theta. In reality, CP and CQ need not be the same. CP and CQ could have completely different lengths. But if P and Q are very close to each other, then we will see that CP and CQ are approximately equal, and that particular value of the length is going to be called as rho, which we call it as the radius of curvature. So, which basically implies that this part PQ becomes part of a circle having a radius rho. If PQ is part of a circle, then PQ is going to be called as arc length, which we call it as delta theta, delta S. So from basic geometry which you have studied in your school days, we will see that delta S is equal to rho delta theta, which is analogous to the equation S is equal to r theta, provided this theta is measured in radians. This equation tells us that rho, the radius of curvature, is equal to limit delta theta tending to 0. What does that imply? P and Q are almost at the same point. Delta S by delta theta is equal to ds by d theta. So your radius of curvature is equal to ds by d theta. Okay, change in theta value. Now we use the chain rule in differentiation. Using the chain rule and treating S to be a function of x and x to be a function of theta, we will be able to modify ds by d theta as ds by d theta is equal to ds by dx into dx by d theta, where x is a variable, theta is another variable. So what we are claiming is s is a function of the x and x is a function of theta as shown in the equation. What does all these things mean? If we had zoomed into that line and we saw that this point is P and the other point is Q, this corresponds to a right angle triangle. We are zooming in. Please remember that P and Q are approximately at the same distance. Hence, the curve between them can be treated as a straight line. Under this situation, if I call PQ length to be equal to delta S, Q to this point, that distance is equal to delta F, and P to this point, that distance is delta X. From the Pythagoras theorem, we will see that delta S squared is equal to delta F squared plus delta X squared, which is a very famous equation. In the limits delta tending to 0, this will work out to be equal to ds squared is equal to df squared plus dx squared, which gives rise to this particular equation. Or if we assume that dx is larger, that is, this distance is quite large in comparison to delta f, we can take the dx outside, and then you will get an equation of this form: ds equal to dx square root of df by dx whole square plus 1. Now, our aim is to calculate how much is ds by d theta actually, which is equal to ds by dx into dx by d theta. So, ds by dx from the previous equation, it will work out to be equal to square root of 1 plus df by dx whole square. So, again, to recapitulate, I'm just stating that this is how the function is going to look like for you. So if I call this one as theta, this angle as theta, from this diagram you can see that tan theta is equal to df by dx. df is a small separate value change in the y value, and dx is basically a change which is happening parallel to x-axis. So what we are ending up with is an equation: tan theta is equal to df by dx, which is very often written as f prime. So whenever you see a prime like this, it automatically implies that the denominator is defined by the variable which will be also given in the definition. If we differentiate this function once again with respect to x, what you're going to get is differential of tan theta into d theta by dx is going to be sec squared theta into dx by dx, as can be seen. Same way, if you take the second derivative of f prime, what we are going to get is d squared f by dx squared only, which is equal to f double prime. Okay. Now let's look at this equation a bit more carefully. We have the famous trigonometric identity 1 plus tan squared theta is equal to sec squared theta. Using that idea, I will be converting the sec squared into 1 plus tan squared theta multiplied by d by dx into d by d theta by dx, as can be seen, and that is going to be equal to f double prime. Or instead of tan theta, you substitute it equal to f prime. We got this equation as 1 plus f prime whole squared into d theta by dx, which works out to be f double prime. Ultimately, you will see that dx by d theta is equal to 1 plus f prime whole square divided by f double prime. This result is arrived at by systematically analyzing pure mathematics. There is no experimentation involved in this. Therefore, our rho, which is basically equal to ds by dx into dx by d theta, works out to be equal to square root of 1 plus df by dx squared, which can be derived from the geometry as we have done earlier, into 1 plus f prime whole square divided by f double prime. How did we get this part? Purely because of the power of the equation which we had been floundering. Okay, so this can be rewritten as 1 plus f prime, because f prime you can retain it as a constant or something which is not changing, is equal to this much plus f prime whole squared to the power 3 by 2. If you do the mathematical jugglery here, it's just one step, you will end up getting this particular result. Hence, the conclusion we are going to get is for radius of curvature rho, geometry determines what should be the value of the elastic constants and things like that, or radius of curvature. The radius of curvature is given by this particular expression 1 plus f prime whole square to the power 3 by 2 divided by f double prime. Here it's important for you to notice the following. Since f prime is a square, whether f prime is positive or negative, the numerator is not going to be having any effect. This will be always a positive quantity. The numerator will be always a positive quantity, whereas f double prime is going to be a negative quantity or positive quantity as the curvature may be. To give you an example of the power of this uh, exam, a power of this experiment, you will be using this equation of the radius of curvature, which we derived here exactly, in studying bending of beams or cantilever bridges. This is a very famous cantilever bridge in Calcutta, the Howrah Bridge. So if you want to study how this thing is going to be bent under the action of a vertical force in this direction, you will be forced into a situation where you have to use the radius of curvature arguments. Okay? The same beam, okay, is used in developing this particular microscopic technique, which is going to be called as atomic force microscopy. Using this particular microscopy, you can actually even image individual atoms in a crystal, okay, provided the crystal is cooled down to or cooled down to very, very low temperatures. Okay. So in such a situation, if you use atomic force microscopy, you will be able to get the pictures of this. For example, on the left side, what you're seeing is quantum dots, quantum arrays, and uh, quantum dots. Okay. So here we are studying quantum dots, and here you are studying atoms, individual atoms. Other places where differentiation is used in physics is basically to study study or model physical systems. In your lower classes, you would have written down a differential equation for the simple harmonic pendulum, which went like d squared by y by dt squared is equal to minus omega squared y. Okay, so that is a second order linear differential equation. Another place where the differentiation is used is in studying the error analysis. And to be very frank with you, I'll expect all physics students to be having some idea about the error analysis by the time they finish 3-year BSc program. With this, I come to the end of the program where we are supposed to teach you the bridge course. Thank you all.